a round of applause.
All right. Hi, everyone. I'm Laurie Kirk, and today I'm going to be talking about writing an iOS decompiler. So who am I? I'm Laurie Kirk. I am a reverse engineer. I specialize in cross-platform malware analysis with a focus on mobile threats, iOS and Android. I also run a YouTube channel called Laurie Wired, where I teach reverse engineering, malware analysis, and all different kinds of low-level programming concepts. Now, we all know what a decompiler is. It takes an application and it tries to decompile to provide an approximated view of what the original source code of the application actually looked like. We all know that there are thousands of applications located on the iOS App Store, and yet there's very little research out there dedicated towards reverse engineering iOS applications. And there is not a dedicated decompiler for decompiling and reverse engineering iOS IPA files. Why is that? Well, it's really hard. There's a lot of different proprietary formats in Apple applications that you have to think about. There's a lot of different challenge that comes into decompiling Mac-OS binaries. We're going to talk about that a lot. We heard a lot about Swift and Objective-C today, and we're going to talk about that even more. But this makes our job as security researchers really, really challenging. Currently, what we have to do for iOS IPA files is we have to take the IPA file, we have to extract the Mach-O binary from that, pass that along to a decompiler, but then at the end of the day, we have to use all these different various tools that run on various different platforms to be able to decompile and disassemble all of the different associated assets inside of the iOS application. So when I was working on this talk, I decided to come up with a goal. I wanted to simplify the iOS analysis process. I wanted to make it accessible across every single different platform and not just limit iOS reverse engineering to security researchers who are currently working on a macOS device at that given time. What this would do is it would allow iOS reverse engineering to be platform agnostic, it would reduce the manual analysis time for iOS applications, and consequently would exponentially, hopefully, increase the amount of iOS research out there that encourages other security researchers to get into this field as well. Which is why, by the end of this talk, I'm going to release a brand new iOS decompiler, open source to the security research community. So let's get right into it. First of all, I talked about IPA files. What are IPA files? They're the main application bundle type for iOS application. They contain our permissions, our resources, the code, all of the different relevant libraries necessary for the iOS application to actually execute. So currently, when we're reverse engineering iOS applications, we follow this kind of step-by-step process. We have to extract the payload, we have to decode all of the different various resource types, and then we still have to locate the main Mach-O binary and the executable inside of the IPA file, and then at the end of the day, we still have to find all of the various entry points inside of the application inside of that Mach-O binary. Now, one thing to note that I see a lot of researchers neglect is there are a lot of different resources inside of the iOS IPA file. We get really excited about executable code and we want to quickly jump into the binary and go through all of the different assembly instructions and understand what the application is doing, but then we're neglecting all of these different resources. Which is why when I'm reverse engineering iOS applications, I like to separate this out into 4 different pillars of analysis. Permissions, resources, the executable binary, and then libraries and frameworks. And all of these are super relevant to the analysis process. So I decided to come up with a plan when I was working on this talk. I wanted to analyze every single pillar inside of iOS applications and try to reverse engineer them on every single different platform that I wanted to be able to support, so that I could come up with an automated, platform-agnostic way to be able to reverse engineer iOS applications. Now let's get into our first pillar, which is permissions. And what do permissions do in iOS? They basically give us a full understanding of what the potential capabilities of the iOS application are. How are they allowed to interface with the user? How are they allowed to interface with the system? There's a lot of really important resources that are part of these permissions. The 2 main resource files that will tell us all of our permissions in iOS are the info.plist and the embedded.mobile provision files. First of all, going to the info.plist, you're going to hear me say plist probably a lot during this talk. You're probably going to go to sleep tonight saying plist in your mind. But it contains all of the permissions that are granted by the user at runtime. So basically what the developers have to do is they have to give a justification to the user as to why they want to be able to have the capability to access the camera, access the location of the user, all this potentially sensitive information that they want to be able to access. They have to provide this inside of this special info.plist. But don't forget about the embedded.mobile provision file. This is also really important. You've also heard a lot about entitlements today. This basically contains all of the entitlements that are granted by the system. So this isn't a request to the user to give these permissions. These are granted by the Apple system itself. And it gives access to sensitive things like iCloud, push notifications, keychain, and we're going to see an example of this later on as well. Now, if we want to go back to formats, there's a lot of issues that we have to talk about here. So let's focus specifically on property lists for now. There are a couple different kinds of formats forplists. There's binary and there's XML, and we have to do a lot of decoding when it comes to plists. But the nice thing about this is this applies to a lot of various different files inside of the iOS IPA bundle. So if you decode a plist on one, it's going to apply to so many different files inside of the application bundle. XML plists are super simple. You can see we have the info.plist here of requesting different permissions from the user, and it's giving the really great justification to access the camera saying, this app requires access to take your photos. Good justification there. But binary plists are not so simple. They have this custom proprietary Apple format. So if we're trying to decode property lists, we have to account for all these different platforms. If you're taking a look at this on Mac-OS, you might even not realize that you're dealing with a binary property list because it's using either PLUtil or any other kind of tool that's automated on the back end, so you have no idea that you're interfacing with anything encoded at all. But you start to notice issues if you start switching to different platforms like Linux and Windows. You have all these different libraries that almost sound exactly the same but are completely different and make you and force you to have to use different tools for every single respective platform that you happen to be working on. So why would you want to have a unique tool per platform? That's going to get really challenging during your reverse engineering process. But the nice thing is that security researchers and reverse engineers, like all of us here, actually exist in the world and have gone through and reverse engineered so many different proprietary formats that are contained inside of iOS applications, including the info.plist. So this is a nice little library that's written in Java, which is cross-platform and runs on all of these different operating systems that I like to support. It's called com.dd.plist or something, and you can basically just import it into your code and be able to handle plists in every single format. And using this library, you can take in a binary property list here, for example, decode it, and get the nice plain text version of it. Now let's go back to our embedded.mobile provision file. The info.plist is important, but we also need to handle all of the different permissions inside of an iOS application. The embedded.mobile provision is actually part plist, but it's also part PKCS7 signature. And these are signed by Apple because remember, these are entitlements that are approved by the system. Now the only thing is, even though this file is super important, there's a lot less research dedicated to decoding and understanding the embedded.mobile provision. So what do we have to do if we want to handle this in a cross-platform method is we have to reverse engineer this ourselves. Luckily, it's actually pretty simple. If you look on the top hand, it's basically just a property list with a certificate shoved there on the bottom. But we don't really care about the certificate. We know that it's designed by Apple, so we can basically just drop that part and extract and decode the property list, whether it's binary or XML, from that file. And then we can get the decoded embedded.mobile provision file and see all of the different entitlements. You see this application in particular is trying to access the keychain, and there's so many different sensitive things that it can do with this kind of access. So now we've completely covered our first pillar, which is our permissions. So let's move on to resources. And these two are really, really intertwined with each other. So the supporting resources can be spread throughout the entire iOS IPA file. And it uses various different proprietary formats that we have to account for when we're trying to decode all of these resources. Sometimes they can be encoded, sometimes they can be in plain text. They can contain metadata, identifiers for bundles, URL schemes. There's just so much different data that can be combined into these. Luckily, we've already coveredplists. We know how to decode these, so we can move on to other different types of resources. One type of resource that I really like to focus on when I'm reverse engineering iOS apps is the localized string files. Now, these are going to be user-facing text that users will see and interface with when they are using the iOS applications. They can contain labels, error messages, developer strings. There's so many useful strings that you want to be able to see if you're reverse engineering the app instead of just focusing on the strings contained inside of the code. These are stored in .strings files, and you can find many different languages that the application supports. For example, if you want to parse out the English strings, you can find the EN file, but there's so many languages that applications try to support as many as possible. But I talked about plists a lot, and if we take a look at these localized string files, that looks a little bit familiar, doesn't it? We can see the magic bytes in the header of the binary property list, plist, right there. So if you take away anything from this talk, and what I take away as I reverse engineered iOS applications during this, is pretty much everything is a property list at the end of the day, which is kind of a good thing because that means it's pretty simple to handle all these numerous resource files that we see inside this gigantic bundle. So localized strings, pretty much already good. But there's a lot of other resources as well that are bundled inside of these iOS applications. We have nib files, zip files, storyboard files that talk about the flow and structure of the application. Now, there's so many different kinds of encodings inside of these, and it would be nearly impossible to keep up all the time with all the different resource types out there, as well as all the different resource types that we could potentially see in the future. So what do we do about this? So I thought, what if we just applied the same methodology that we use when taking a Mach-O binary apart and having a minimum number of characters that we now count as a string, but instead of just doing that, focusing on the executable, we could apply that same process across every single different resource file using just a little bit of magic with regular expressions. And it can look something like this. This works on property lists. This works on so many different file types. We basically just parse out anything that looks potentially like a string, but we can include this so that reverse engineers can easily see all potential strings inside of the application instead of just those from inside of the Mach-O binary. So now let's move on to our third pillar. This is probably the most exciting pillar for most people here. And of course, this takes us right back to property lists. I did say I was going to say that a lot during this talk. But I promise that it is relevant. We have to look at the info.plist to be able to find the name of the main executable binary for this particular application. For example, if you see here, I was reverse engineering Flappy Bird because it's fun. And if we take a look at the CF bundle executable, this is a special tag inside of the info.plist, we can see that the main Mach-O binary name for this is flap. But our analysis doesn't get to end there. We don't just get to take that and decompile that. We have to account for universal binaries, historically called fat binaries. Now, it's really simple to be able to parse the fat header really luckily. Now, this does have a lot of tools that are, again, proprietary to macOS, but it's pretty simple to be able to automate this process, again, inside of a cross-platform language like Java, to be able to parse the magic header, try to see what architectures this particular universal binary supports, and extract the associated slice from this binary that we would like to analyze. In the fat header, it shows all of the different architectures as well as the offsets to the locations of these. So it's pretty trivial to be able to parse out and separate the universal binaries. And if we do this, we can see we can just basically extract the slice that we're interested in and then pass this to a back-end decompiler. I'm using Ghidra, for example, in this case. And here we have it. Here we have the code. This is basically just a Mach-O binary taken from an iOS application that I passed directly to Ghidra, and it looks really, really good, honestly. We have all of our methods kind of labeled. We can see the namespaces, and this is pretty promising. On Mac, This is not so nice if you try to take a look at it on Windows. This really, really stinks because if you look at it on Windows, none of the classes are actually defined. We're basically just shoving every single method inside of the application under this one global class that doesn't actually exist inside of the Mach-O binary. It's just Ghidra struggling to try to show us what it thinks it could be, but it has no native support for Swift or Objective-C. So I thought, how am I supposed to handle this? This is kind of like a wrench in the road. How am I supposed to reconstruct these classes? So I thought, what if I parsed out the method names and tried to reconstruct the classes from these and just associate the decompilation with my newly reconstructed classes, still using a back-end decompiler, but now adding my own kind of analysis on top of this? And if I use an abstract syntax tree and I can parse out the method and class names, I can keep track of all of the variables, methods, class names, and statements inside of the application and basically create a brand new hierarchy for what I think this actual application looks like. And I used the help of a C++ grammar to be able to handle object orientation. Since decompiled C and Ghidra, it's not really like object-oriented, but Swift and Objective-C are. So we get into like these really, really weird kind of half object-oriented, half not kind of decompilation. But there's one more thing that we have to account for. We have to be able to account for Swift and angled names. There was another talk earlier that made me really, really hate how Swift handles strings and names, and yes, we all have to account for these. They're very painful. But it's not too bad. Basically, if we take the method name inside of the application, we can follow the standardized structure and parse out both the class name, the method name, as well as the return value and the parameters for that method. So if we do that and we use the help of our abstract syntax tree, we can create this brand new structure and this brand new created hierarchy of our iOS application. You can see we've parsed out like the Swift UI class, which contains so many different methods inside of it, and as well as the control flow flattening class, which was one of the main entry points to this particular application. So we have this brand new structure and hierarchy that we're able to work with. And the best thing is this will work across any different platform that you're trying to reverse engineer on instead of just relying on native macOS capabilities. But the question is now that we have all this information, where do we actually start our analysis? If you notice, iOS applications are really, really large. Actually, just Mac applications in general are pretty large. And we're also going to talk about that very shortly. Fortunately, there's a well-documented standard structure for iOS applications. They follow something called the application lifecycle, which is basically just a fancy way of saying different events happen. Let's say the application goes to the foreground or the background, and the system automatically triggers respective methods and respective code that needs to execute and handle the different potential states of the application. So every single one of these we can count as an entry point to the application. Instead of having one unified kind of entry point, we have to account for all of these different various entry points in the application to handle all of the different potential application states that we might go into. But that means that we can use all of these as a different entry point to begin our analysis and then analyze the child methods that this potential entry point might call during this. So it's kind of like having a million different main functions instead of having our one particular main function. And in fact, if you take a look at these lifecycle methods and you look at like application did go into the background, for example, that is a perfect kind of place to slip in something kind of nefarious. So now we've talked about permissions, we've talked about resources, we've discussed how we can try to find potential ways to automatically decode all of them across platforms. Let's talk about something really important, libraries and frameworks. So I mentioned it earlier, but why are iOS applications so large? If you have tried to take a Mach-O binary from an iOS application and drop it into like Ghidra, for example, or your favorite decompiler, you notice that you walk away for 20 minutes, you go get a cup of coffee, you come back, and it's still decompiling. Like you could be there all night, and it will still take forever to decompile. So what is the reason for that? Well, the primary reason is that a lot of third-party or Apple frameworks and libraries come bundled inside of the application, making it extremely challenging to be able to differentiate between user code that you're interested in and then library code that you really do not want to waste time reverse engineering. You can see this example right here has so many different classes. These are just the classes. Each one of these has tens to hundreds of child methods underneath this, and it basically just keeps going on for what feels like ever. So we're going to do our hands-on, and we're going to wait for an app to decompile to demonstrate how long it takes to decompile iOS apps. And this should take probably 5 minutes, I would say, the rest of the talk. No, just kidding. What we're going to do is we're going to figure out how we can distinguish between user code and library. And actually, the answer is incredibly simple, but I think it's super relevant to be able to understand and talk about the way to distinguish between this. Probably the most obvious answer is the correct answer. Basically, take those demangled names that we spent so much time working on and reconstructing, and look them up and see if anybody has created a guide and a reference for the library or framework online. Developers really want you to use their libraries and frameworks, so they'll usually document them pretty well. So that way, we can end up reading documentation instead of decompilation to be able to see what the developer says the method is supposed to do versus trying to spend a ton of time reverse engineering really ugly C code to figure out what this library code does, only to realize that it's a library that we don't care about. So we talked about runtime, we talked about libraries and frameworks, but we need to talk about something really important as well, runtime methods. They look really annoying in Objective-C and Swift. You can see we have a lot of different ones shoved inside of here, highlighted. They look something like this. These are some really popular ones in both Objective-C and Swift. Basically, they're implemented by the system, and they are used dynamically to invoke other methods at runtime, and these basically take in a parameter as a string of what method they're trying to invoke. It looks a little bit complicated when you're trying to decompile an application. You can see on top we're calling some Swift runtime methods Swift get class name, but luckily we have a plain text string as a parameter. So if we take a look at the strings and we're able to reconstruct those, it's really simple and trivial to realize that all this is doing, the top 2 lines, is just creating an instance of the class called myClass in this case. So now we've analyzed all of the different pillars of iOS applications. We've looked at the permissions, we've looked at the resources, we've looked at the executable and all of the libraries and frameworks, and we've been able to create a standardized automated way of handling every single resource inside of the IPA file using Java to run on every single platform. But one more thing. This is really ugly to look at. If you take a look at this function, it basically just goes on for way, way too long, and you have to take a look at all of the different runtime methods, all of the different library code, and it's really challenging to be able to compress this and get a quick view and idea of what the overall behavior of the application actually is. So what we can do is we can take the decompiled pseudocode that we worked so hard to reconstruct, we can pass it to an LLM on the back end, and they're very, very good at language processing and language translation, hence why it's directly inside of the name, and we can ask it to produce either a Swift or an Objective-C approximation of what it thinks the code actually looks like in the native language that the application was written in. And it does look really, really good. It creates a very good approximation of what the code is. It's not going to be 100% accurate, but it's going to potentially save you like hours and hours of research to be able to get a quick idea of what the application is doing. Which is where I would like to introduce Malimite, which is a brand new iOS decompiler. Malimite runs on Mac, Linux, Windows. It has direct support for IPA files. You can simply drag and drop an IPA. It automatically decodes all of the resources on the back end, avoids library code, reconstructs classes, and has a built-in LLM method translation tool to allow you to reverse engineer your apps inside of the native languages instead of looking at really ugly C code. So let's do a very quick demo, and let's show Malimite. Probably, if the demo gods will allow me to. Here we go. All right, we don't want emojis. There are no emojis part of Malimite. What we're going to do is we're going to load an existing application to avoid spending time watching me decompile an app. We see our decoded info.plist right here, which has all of the strings for you. We have the embedded.mobile provision, as well as all of the resources. And if we want to take a look at a function, I'm going to specially pick a particular function. And we're going to look at a function inside of the recording coordinator class. And let's pick a specific method. I think I'm going to pick recording URL. Take a look at this. We have all of this ugly code inside of here. So what if we take our function, select it, pass this on the back end to GPT-4 Turbo, and what I'm doing right now is basically asking it to translate this to the native language, which I have detected is Objective-C. So now you do get to stare at me for a second while this is processing and sending this back as a request to receive the translated method back so that we can replace this inside of our code. Again, if the demo gods will allow me to do this. I'm running on my hotspot right now, and I've been using this all day, so I'm probably at the very end of my data. It appears that I am at the end of my data, so we will go to the magic portion of this and pretend like this did actually work. So if we do this and pass it back, it will give us a view that looks something like this. And we have the native version of this code. So with that, now go decompile some iOS applications, and you should be able to solve this. Here is a link to the GitHub repository that hosts the Decompiler. Feel free to have fun and go decompile some iOS apps. Thank you so much.